Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in class 12th physics, in the chapter electric circuit, we will make core understanding of series parallel simplification of resistive circuits, and we will learn how to identify resistors in series as well as in parallel and produce clarity in their simplification. So let's start. In any circuit, different resistors are connected together in different formats. When resistors are connected in simple series or simple parallel configuration, we can replace a combination of several resistors by a single equivalent resistance. And when the entire circuit becomes a single resistance, we can apply Ohm's law, and out of current and voltage, if we know any one, we can find out the other parameter, and that calculation is used to simplify series parallel resistive circuits. V is equal to IR product is Ohm's law, and the only limitation of this relation is that it is applicable to only a single resistance current and its voltage. So when several resistances are connected in series or in parallel, we have to find out their equivalent resistance, whether they are in series or in parallel. And now on this single resistance, we can apply Ohm's law, and out of voltage and current, if one is known, we can find out the other one. To find out current through these series connected resistances, we can obtain current of an equivalent resistance using Ohm's law, as across A and E terminal, when 40 volt is applied to these four series connected resistance, where equivalent resistance of series connection is 10 ohm, then 40 volt will produce 4 ampere current in 10 ohm resistance, and this current of equivalent resistance is also current of all individual series connected resistances. So current in 1 ohm is 4 ampere. So voltage across C and D terminal from Ohm's law, V is equal to IR calculation, will be obtained as 4 volt. In parallel connected resistors, the voltage applied across combination is the same for all resistors, and if that common potential is known, voltage across A and B terminal is given 30 volt, then that 30 volt is voltage of 5 ohm or 6 ohm or 10 ohm or 30 ohm, and from that 30 volt information, current of 10 ohm can be obtained by Ohm's law as 3 ampere. But if in parallel connected resistors, voltage is not known to us and the total current passing through parallel equivalent circuit is given, then we can replace all parallel connected resistors by a single equivalent resistance, and now we can apply Ohm's law to find out voltage across parallel equivalent, and the voltage obtained by Ohm's law in parallel equivalent resistance is also the voltage of all individual resistors connected in parallel. So 15 ampere in 2 ohm produce 30 volt. So 30 volt is voltage of 5 ohm, produce 6 ampere current in it. Similarly, 30 ohm would have 1 ampere current through it, as voltage of equivalent resistance is voltage of individual resistance in parallel connection. It is also very important to identify series connection of resistors or parallel connection of resistor in a given configuration of resistances in a complex electric circuit. If all resistances connected together have a single current flow path, all have the same common current passing through them, and the total voltage applied across this combination is divided among all these resistances of common current path, then we say this configuration of resistors, as here in given circuit, 3 ohm, 2 ohm, 1 ohm and 4 ohm, are in series. Suppose two resistors have the same current, but the current path is not common, then we won't say that they are in series. If at a certain junction in electric circuit, division of current takes place, and this divided current once again assemble at another junction, then at these two junctions, as here across A and B, all branches which are connected together are in parallel, as the potential across A and B is the potential of all these branches. So 5 ohm, 6 ohm, 10 ohm and 30 ohm are in parallel to each other. But if current division takes place at a junction, but the voltage of two elements, as here 6 ohm and 10 ohm is not the same, then we won't say 6 ohm and 10 ohm are in parallel. This divided current assemble at another point, say at B, then we will say the voltage of 6 ohm and voltage of this 10 ohm and 2 ohm series combination is the same, and current division takes place in these two sections. So 6 ohm and this 12 ohm are in parallel to each other here across A and B in this circuit. we'll understand the concept of series parallel circuit simplification with some examples. Let's start with one. Here in this circuit, we have given 6 resistances and we have to find out current in all those 6 resistances. So for series parallel identification, we have to draw current flow diagram in this circuit, find battery position in the circuit and identify the high potential terminal, and the current will live out of voltage source from high potential terminal and travel in the circuit, and finally the current will travel towards negative low potential terminals. Now here at junction A, current leaving from high potential and divide in 2 branches, and these 2 branches current assemble at junction 2 here, and then it travels towards negative end of battery as shown here in this diagram. So we can say that at A junction and B junction there exists 2 path of current flow having same potential and division of current. So here in this circuit, across these 2 junction A and B, there exists 2 current flow path having identical potential across A and B, and current get divided among the 2 such sections. So these 2 sections across A and B are parallel to each other. In the path ACB, there is only one current flow path, and the 2 resistance 6 ohm and 12 ohm are in series to each other as they have the same current, and the total potential across A and B divides among them. So their equivalent resistance is sum of individual resistance. 6 and 12 summation is 18 ohm. Similarly, in other path ADEB, there exists the same current flow path, and these 3 resistance 4 ohm, 3 ohm and 2 ohm are in series as they have the same amount of current, and total voltage across A and B divides among these 3. So their equivalent resistance is summation of individual resistance 4, 3 and 2 summed up as 9 ohm. So this series combination of 6 and 12 ohm will be represented by a single resistance of 18 ohm across A and B, and similarly in other branch 3 resistances 4, 3 and 2 ohm are equivalently represented by a single series equivalent resistance of 9 ohm across A and B, and the simplified circuit will be as shown here. Now in this simplified circuit at junction A, current divides in 2 branches of 18 ohm and 9 ohm, and the same current assemble at junction B. So across 9 ohm and 18 ohm, the voltage is the same and current divides. So these 2 resistance 9 ohm and 18 ohm are in parallel to each other. So the total equivalent resistance of these 2 is given by product by sum, and simplification will give that equivalent single resistance value 6 ohm. So the 2 resistance when replaced by a single resistance of 6 ohm, the simplified equivalent circuit will become as shown here. Now if we analyze current flow in this diagram, current leaving from positive end of the battery passes through 6 ohm, and then the same current path have 1 ohm resistance in their circuit. So the 6 ohm and 1 ohm got the same amount of current, and the total circuit voltage 42 volt divide among the 2. So 6 ohm and 1 ohm are in series, and their series equivalent will become as sum as 7 ohm. And in that single 7 ohm resistance, as per Ohm's law, current voltage divided by resistance will result in 6 ampere. And this 6 ampere of total equivalent 7 ohm resistance is also the current of 6 ohm and 1 ohm, as in series current of equivalent resistance is the same as current of individual resistances. Now this 6 ohm is a parallel equivalent of 18 ohm and 9 ohm, and for parallel connected resistances for analysis we need voltage, and to find out voltage we can use voltage of equivalent resistance, and in this 6 ohm resistance the total current is 6 ampere, and total current in parallel equivalent resistance of 6 ohm produce 36 volt, and the voltage of equivalent resistance is the voltage of 9 ohm and 18 ohm. So current in 9 ohm is voltage divided by resistance, and it is 4 ampere, and we know this 9 ohm section is a series connection of 3 resistance 4 ohm, 3 ohm and 2 ohm, and we know in series the current of equivalent resistance is current of individual resistance. So current of 2 ohm, 3 ohm and 4 ohm would become 4 ampere, and similarly this 18 ohm, which is a series combination of 6 ohm and 12 ohm, have voltage 36 volt and its current is 2 ampere, and the current of 18 ohm is also the current of 6 ohm and 12 ohm. So we have obtained current of all resistances. We have given 3 separate resistance 1 ohm, 2 ohm and 3 ohm, and we can combine them in all possible manners, and we have to find out corresponding equivalent resistance with the use of these three resistances, and we have to also find out the combination which results in 11 by 3 ohm value, 11 by 5 ohm value, and 6 by 11 ohm value. So we can connect all three resistances in a series, and in series the total equivalent resistance is sum of individual resistance, and it results in 6 ohm, and that is the maximum possible value of resistance with these three resistances if they are connected in series. Now we can also connect all three in parallel, and when we connect all three in parallel, they would have same voltage and the total current divide among them, and in that case the inverse of equivalent resistance is sum of inverses of individual resistances, and 1 ohm, 2 ohm and 3 ohm when inverted and summed up and LCM is taken, then this become 11 by 6, and when we invert to get equivalent resistance, then we'll get equivalent resistance 6 by 11 ohm. That is minimum possible value of resistance with these three resistance values, and this third option answer is if we connect all three resistances in parallel, we'll get 6 by 11 ohm value. We can connect these three resistance as one in series with a parallel combination of other two resistances, and there could be three such combinations. Now in this combination 3 ohm and 2 ohm are in parallel to each other. Their equivalent can be obtained by product by sum analysis, and 1 ohm in series will give the resultant equivalent resistance. When we take LCM, this become 11 by 5 ohm. Similarly, with 2 ohm as single resistance and two resistances 3 ohm and 1 ohm parallel to each other, but in series to 2 ohm will results in the equivalent resistance of 3 ohm and 1 ohm product by some calculation results in 3 by 4 ohm value, and 2 ohm in series with it by LCM results in 11 by 4 ohm value. And similarly, if we put 3 ohm alone and other two resistance 2 ohm and 1 ohm are connected parallel to each other, and this parallel combination is in series with 3 ohm, the parallel equivalent of 2 and 1 ohm is product by some calculation 2 by 3 ohm, and 3 ohm in series with it when LCM is taken, the sum will become 11 by 3 ohm. So the three combinations results in 11 by 5, 11 by 4 and 11 by 3 ohm values. Three resistances can be connected together with any two resistance in series to each other, and the third resistance parallel to that series combination. So here 2 and 3 in series become 5 ohm, and 5 ohm in parallel to 1 ohm product by some calculation results in value 5 by 6 ohm. Similarly, when 3 ohm and 1 ohm are in series and 2 ohm is connected parallel to that series combination, then 1 and 3 series combination is 4 ohm, and 2 ohm parallel to it product by some calculation result in single equivalent resistance 8 by 6 ohm. And similarly, when 1 and 2 ohm are in series and this series combination got 3 ohm parallel to it, then 1 and 2 series combination is 3 and 3 parallel become 1.5 ohm. 9 by 6 when simplified will result as 3 by 2 or 1.5 ohm value. So when identical resistance are in parallel, as here 3 and 3, then their equivalent will become half. In this circuit, three identical resistances between A and B got two short circuit connection, one at upper position, second at lower positions, and we have to find out equivalent single resistance value between A and B. In this circuit, these three resistance looks like they are in series connection, but in actual practice they are connected in parallel to each other, and we can visualize this. If this upper short circuit path between A and B and lower short circuit path between B and C is treated as point, and this D end of resistance, this R and this R, is separately connected to A position. So this D end is connected to A, and the D end of this resistance is also connected to A separately. Similarly, this C point is connected to B. So this C end of R resistance is connected directly to B position, and similarly C end of this resistance is connected to B position directly without interconnection in between. And when we reshape the circuit, we find that B and C are at same position and A and D are at same position, and all three resistances are got same two end positions. All three got one end connected together and other end also connected together. So these three resistance, as it looks in this green highlight, are parallel to each other, and their equivalent resistance will become 1/3 of R by 3. Here in this circuit, 8 resistances are connected together in a typical combination, and we have to find out equivalent resistance between terminal B and C in first part, between C and D in second part, and between A and D in this third part. So let's solve the same circuit for 3 different conditions. To find out equivalent resistance across B and C in the circuit, assign incoming current at one terminal and outgoing current at second position, and we check current flow from high potential to low potential as shown in this figure. We find that this 3 ohm resistance got only one wire connection and it's not a part of complete circuit, so there won't be any current flow in this 3 ohm. So it can be isolated from remaining circuit, and remaining circuit across point B and C is once again visualized as this circuit, and in this circuit at position B and C current divides in 3 positions, 3 parts. So this 5 ohm, 10 ohm and 30 ohm got identical potential and current divisions. So these 3 resistance 5 ohm, 10 ohm and 30 ohm are parallel to each other. Similarly, between F and E point, 2 resistance 3 ohm and 6 ohm have current division, and the current again assemble at other position, so they have same potential and division of current. So 3 ohm and 6 ohm are parallel to each other. We can find out parallel equivalent of 5 ohm, 10 ohm and 30 ohm as this calculation. The inverse of equivalent resistance is sum of inverses of individual resistance 5 ohm, 10 ohm and 30 ohm, and when LCM is taken and calculation is simplified, the equivalent resistance can be obtained by inversion, and 30 by 10 will become 3 ohm. So 5 ohm, 10 ohm and 30 ohm in parallel are equivalently represented by a single resistance of 3 ohm. Similarly, 3 ohm and 6 ohm, two resistance parallel to each other, got a equivalent resistance product by sum 3 and 6 when multiplied and divided by 9 results in 2 ohm value, and this 2 ohm, 4 ohm and 1 ohm got a same current flow path, and total voltage of B and C divides among these 3 resistance. So 1 ohm, 4 ohm and 2 ohm in series become equivalent to single value 7 ohm, and that 7 ohm now is parallel to 3 ohm, and equivalent resistance across B and C can be obtained as product by sum calculation 2.1 ohm. Now in the same circuit we have to find out equivalent resistance across these two terminals C and D. And once again, when we analyze current flow path, current enters at high potential and at C position there is a division of current once in 2 branches and then again in 3 resistances 5 ohm, 10 ohm and 30 ohm, and this divided current assembles at position B and then flow as shown here. Now once again this 3 ohm resistance got a single wire connection and it's not a part of complete circuit, so it can be isolated from this remaining circuit for analysis sake. Now these 3 resistance 5 ohm, 10 ohm and 30 ohm got same potential across them and total current divides among them. So these 3 are parallel to each other and their parallel equivalent will become 3 ohm. Similarly 6 ohm and 3 ohm are parallel to each other and their single parallel equivalent is 2 ohm. Now this 3 ohm, 2 ohm got a single current flow path and 1 ohm and 4 ohm again got a single current flow path. So 3 and 2 ohm in series become 5 ohm and similarly 1 ohm and 4 ohm in series become 5 ohm, and these two 5 ohm branches are parallel to each other across C and D. So single equivalent resistance across CD is product by sum and it results in 2.5 ohm value. Now in the same circuit we have to find out single equivalent resistance across terminal A and D. If A is high potential terminal and D is low potential terminal, then current flow in this circuit represent a division of current at terminal B and assembly of those currents at position C. So across B and C, these 3 ohm, 5 ohm, 10 ohm and 30 ohm are parallel to each other. Similarly, between F and E, there is a division of current and that again assemble at E position. So voltage of 3 ohm and 6 ohm is same and current get divided among the two. So 3 ohm and 6 ohm are parallel to each other. Parallel equivalent single resistance value of 5 ohm, 10 ohm, 30 ohm is 3 ohm, and similarly 6 ohm and 3 ohm parallel to each other become a single resistance of 2 ohm. Now 3 ohm, 1 ohm and 4 ohm got same current flow path, identical amount of current, and total voltage across B and D divide among 3 ohm, 1 ohm and 4 ohm. So these 3 resistance become a single series equivalent resistance of 8 ohm, and 8 ohm and 2 ohm got division of current and same potential, so the 8 ohm and 2 ohm parallel to each other got a equivalent resistance product by some calculation, and the parallel equivalent of 8 and 2 is in series with 3 ohm, so the resultant equivalent resistance become 3 and 1.6 equal to 4.6 ohm across A and D terminal in this circuit. In last 20 minutes, we have explained how series connected resistances and parallel connected resistances are identified and simplified. And now you can handle any series parallel simplification problem asked in senior secondary physics examination. Our other learning videos of the same playlist are equally useful to enhance your subject understanding and core competency of physics knowledge, and they will improve your exam score. If you find our work useful, do share it with your friends. Happy learning. Thank you very much.